Now, we're going to talk about describing the relationships using least squares regression. And you've likely done regression before. It's where you have some scatter plots or a lot of points on a scatter plot and make a line to fit those points as best you can. We'll talk about why it's called least squares later on. So here's what we're going to try to do in this section. And we are breaking this into 4 pieces, but we're going to, over the whole section, interpret a regression line, calculate the actual equation of the least squares regression line, calculate the residuals, construct and interpret residual plots. These are actually very helpful in knowing things about our data, as you'll see. And then determine how well a line actually fits the observed data. And finally, interpret computer regression output. So it's great that technology can do a lot of this for us, but knowing how to use and how to interpret the information the technology gives us matters. So a regression line is a linear, meaning straight line relationship between 2 quantitative variables. That kind of relationship is common and it's fairly easy to understand. A regression line summarizes the relationship between 2 variables, but only in settings where one of the variables helps explain or predict the other. So here's our official definition. A regression line is a line that describes how a response variable y changes as an explanatory variable x changes. We often use a regression line to predict the value of y for a given value of x. So it tells us how does y change as x is changing. And this points out one of the biggest perks and reasons they do it is it allows us to use the information we already know to then predict things we don't know, whether it be because it's in the future or just a different value than we see, anything like that. So if you want to look at page 165, or you can see it here, there's a scatter plot of the change in non-exercise activity and measured fat gain after 8 weeks for 16 healthy young adults. And as you look at the plots, the scatter plot, the plot shows a moderately strong negative linear association between NEA change and fat gain with no outliers. Though truthfully, as I look at it, I don't know if you can see where my mouse is, that one looks like it's a possible outlier to me. It's just the farthest away, but there's certainly nothing that's extremely far out there. But the regression line does predict fat gain from the change in NEA. So just remember, we're still going to talk about the strength, direction, and form. So we call it moderately strong because the points are relatively close together. Negative because we're heading down as we move left to right. In other words, as one of these goes up, the other one goes down. As non-exercise activity increases, fat gain decreases. And it is generally a linear shape. So we can interpret this, looking at this one point they said, when non-exercise activity is 800 calories, then our line predicts the fat gain of about 0.8 kilograms after 8 weeks. So make sure you are able to interpret things like that with these problems. We want to make sure it's not just numbers we're talking about, we actually know what these numbers mean and what they tell us. Speaking of it, now we need to talk about interpreting a regression line. A regression line is a model for the data, much like density curves. The equation of a regression line gives a compact mathematical description of what this model tells us about the relationship between the response variable y and the explanatory variable x. So it is about the relationship between the 2 variables. So here's our definition. Suppose that y is a response variable, meaning we'll plot it on the vertical axis, and x is an explanatory variable, plotted on the horizontal axis. A regression line relating y to x has an equation of the form y hat equals a plus bx. So I want to pause right there. It's not incorrect if you do bx plus a. I mean, that's closer to the mx plus b form I know we're used to. But it is normal in stats that they do the constant first and then the bx second. And the reason for that is while we won't have to worry about things beyond linear right now, so you don't have to worry about that. in statistics, when they start doing things like quadratics or cubics, they just like how it kind of keeps things in order. So you have constant and then x. If we want to add a quadratic term, you just tag it on at the end. So then it'd be plus cx squared and then plus dx cubed. So they tend to like that just because then if you're adding more terms, you're just adding them on to the end of that. That tends to be why they use that pattern. So I'd encourage you to please use this of using the constant first a plus bx, but it doesn't mathematically really matter which one you write first. Alright, but in this equation, y hat is the predicted value of the response variable y for a given value of the explanatory variable x. So it's important, very important, you use y hat, because we're not saying, the reason there's a difference is we're not saying this is the actual value of a y that we found in our data. We're just saying this is the value that is predicted by our line. Now there are times those will be exactly the same thing, but there's also plenty of times where it won't be the same thing. So when we're talking about y, we're talking about an actual value we found in our data. Y hat is the predicted value given our regression line's equation. B is the slope. You know about that. That's the amount by which y is predicted to change when x increases by 1 unit. So we are going to be asked to interpret the slope. And big picture, generally, or just looking at the general way to interpret it, is that what's written right there. That is how much y is predicted to change when x increases by 1 unit. So if you can just plug that idea in your head, when they ask you to interpret it, it'll really just be remembering that, but then actually saying what y is and saying what x is, and being specific about the unit is helpful as well. A is the y-intercept, and again, this is telling you generally what it is every time. The predicted value of y when x equals 0. This can also be described as the initial amount. So when they ask you to interpret these things, all you have to do is put these things in context. So first, let's try this. Actually writing an equation. So a zealous AP Math teacher believes that a student with a current math SAT score of 480 can increase their score by 20 points for each month that they attend his review sessions. Now, what is the equation of the teacher's regression line for predicting the math SAT score from time in his review sessions? So as you're trying to write this equation, make sure you think about what we just looked at as the definitions for the slope and the y-intercept. And if you can keep what those mean in your brain, that should make it pretty straightforward on how to write an equation for this. So please pause right here, give everyone a moment to consider the equation, then press play when you're ready. Should have y hat, don't forget the hat, y hat equals 480 plus 20x. We use 480 for the y-intercept because we know the initial amount of their SAT score, or how much it is when there are no months that they've been to the review session. In other words, when x is 0, their score is 480. 20 is the slope because that's how much the predicted y, their score, increases per unit of x, meaning per month of review session that they attend. So as their months of review sessions increases by 1, their predicted score increases by 20 on the math part of the SAT. So interpreting the regression line, we're going to try that here with this same thing on non-exercise activity and fat gain. So here we have the equation. 3.505, that's our y-intercept, and then negative 0.00344 is our slope. And notice they went ahead and just put what the variable is. Instead of just saying y hat, they just said fat gain hat. And instead of just saying x, they said NEA change. So that helps us see exactly what we're talking about in this particular problem. So the slope tells us that the amount of fat gained is predicted to go down 0.00344 kilograms for each added calorie of NEA. So again, if we just broaden it, it's how much y is predicted to change, and it is important to say the predicted part, how much y is predicted to change as the x value goes up 1 unit. So in context then, this is how much the amount of fat gained is predicted to change, in this case go down because it's a negative slope, and we put the amount, 0.00344 kilograms, for each calorie, just 1 calorie, of NEA. Then the y-intercept, 3.505, is the fat gain estimated by this model if NEA does not change when a person overeats. So when the x value, the NEA change, is 0, that's what we predict the fat gain to be. It's our predicted value of y when our x value is 0. So when NEA change is 0, that's what we predict the amount of fat gain to be. We also can use this to predict things. So while we have the data that's there on the scatter plot, we might want to predict what happens at places where we don't have data. So we can use the regression line to predict that. So you can see here they wanted to predict it when the NEA is 400 calories, what the fat gain would be. To do that, you just have to plug 400 in for your x value, the NEA change, and then work it out. So we predict the fat gain to be 2.13 kilograms if the NEA change is 400 calories. And we were able to predict that based on the data using the regression line. And that's just the interpretation right there. We predict a fat gain of 2.13 kilograms when a person with NEA, or when a person has an NEA of 400 calories. Extrapolation. Here's a place we have to be careful. It's completely fine, and part of the reason we do regression lines, to predict the response y hat for a specific value of the explanatory variable x. But the accuracy of the prediction depends on how much the data scatter about the line. While we can substitute any value of x into the equation of the regression line, we have to be careful about what we do, and we're going to talk about why and in what ways. Extrapolation is when you use a regression line for prediction far outside the interval of values of the explanatory variable x used to obtain the line. Such predictions are often not accurate. So if you look back at our graph with the NEA and the fat gain, I think our graph shows things around 0 to 1,000. So certainly we could say, all right, well, what if their NEA changes 5,000 calories? I mean, mathematically, you can plug 5,000 in for x, and it's going to give you an answer, but our data only fell in the kind of 0 to 1,000 range. 5,000 is way beyond what our data, which is what we use to create the line, 5,000 is way outside that range. It doesn't mean you can't go just outside. So if our numbers are 0 to 1,000 and you want to know what's going to happen at 1,200, that's reasonable. That's relatively close. But something like 5,000 would be extrapolation, and we need to avoid that. Something that's very far away from the data we have, it's not appropriate to use it because there may be other things that factor in when the numbers are far different from what you already see. So in summary, don't make predictions using values of x that are much larger or much smaller than those that actually appear in your data. Just to make sure it's clear, it doesn't mean you can't go outside it at all. It's just saying you can't go far outside it. It's okay to go a little bit beyond it either direction. That's part of the benefit of it. But you shouldn't go very far either direction. Okay, assuming everything's going according to plan, this is the last video you have to watch from me. You'll get to actually see me do it in person soon. I hope that's a good thing. I missed you guys. Hope you're doing well.